I teraz będzie kolejny wykład po angielsku. Nasz gość ze Stanów Zjednoczonych, tym razem syn, dr Louis Jensen, który powie na temat różnic między sztuczną inteligencją a ludzką inteligencją. Natomiast co do samego prelegenta, to urodził się w mieście Bismarck. Studia skończył na Uniwersytecie Notre Dame z fizyki i z fizyki nuklearnej, a następnie przeniósł się do Bostonu, gdzie skończył informatykę i specjalizuje się w sztucznej inteligencji, w deep learningu. Było o tym, myślę, że będzie dobre do powiedzenia.
Okay, so the topic of this talk will be how computers and humans think both similarly and differently. I'm going to approach this from an engineering perspective, largely. My degree is in computer science. It's a problem that includes a philosophical aspect and an engineering aspect, and I think both are very important to talk about, but my area of expertise is more in the engineering side. So in order to answer this question, first I want to give you a brief overview of deep learning. And that is because deep learning is the current state-of-the-art, the best we've got in artificial intelligence, or in computers thinking. So what is deep learning? Well, in the 1940s, British computer scientist Alan Turing said, what we want is a machine that can learn from experience. Entered machine learning, and more specifically, deep learning would come to be the dominant technique used in this field. The idea is that there are two sort of main camps to artificial intelligence research. There's one that's based on this idea of learning from experience. The computer will somehow have input data and output data, and it will learn over time. It will self-adjust. It will self-optimize to improve itself. The other idea of artificial intelligence, or the other sort of school of thought and camp, is that a human will encode what we know into the computer and put it into the computer, and then the computer will be able to use that well also. These two schools have sort of competed over the last 70 years in artificial intelligence. Currently, deep learning is what dominates the field. It's the current state of the art, and it far outperforms the older techniques of humans coding into the computer. So this idea of computer self-adjusting has turned out to be very powerful. The idea originated when Donald Hebb, a neuropsychologist, decided that he wanted to simulate, crudely approximate, or mimic what goes on in the human or in the animal brain on a computer. And he noted that neurons, we have neurons in the brain, and they're connected by synapses, and neurons that fire together, wire together. They're more likely to fire together in the future. The electrical signal goes from one neuron through the synapse to another neuron, and it was theorized that this had something to do with the learning process. And so he crudely simulated this on a computer. Since then, Hebbian learning has been replaced by something with some similarities called back propagation, but the concept is largely still the same. Neurons that work well together are connected more strongly over time. In the 1960s, a more complex multi-layer perceptron model was chosen. Oh, can everyone hear me? Oh, okay. Is this better? Or? Oh, much better? Okay. Sorry about that. In the 1960s, the multi-layer perceptron model was developed, a more complex model, and then there was something of a dry spell where deep learning sort of took a backseat, and this was largely due to computer hardware constraints. So the computer hardware needed to catch up to the theory in order for deep learning to take off. The later history of deep learning is actually quite recent. In 2009, a paper was published that used graphics processing unit technology to train deep neural networks, these artificial simulations trying to approximate the animal brain, the biological neural network, artificial neural networks on a computer. A graphics processing unit you can think of as a central processing unit, which you all have on your computers and phones, except your central processing unit might be quad core or dual core, so it can do 4 things at the same time or 2 things at the same time. But a graphics processing unit can do 1,000 things at the same time, but it can only do very simple things. So it can do addition, multiplication. But this is very useful for deep learning technology, since there are many different artificial neurons and many different interactions that need to be simulated. So what is it that deep learning can do? Well, that first paper used deep learning for image classification. And so it took a data set of images and classified those images as dogs, cats, airplanes, all sorts of different things. It turned out the data set had 1.4 million images in it. It's called the ImageNet data set. It's publicly available in 2,000 different categories of things: dogs, cats, planes, and so on and so forth. And the deep neural network classified these images with human-level performance, identifying correctly which images had dogs, cats, and so on and so forth, which is something that previously could not be done with computers with the older artificial intelligence. And so that began this explosion in 2009, that began this explosion, and ever since, in the last 15 years, deep learning has done more and more impressive things. Here we see an example of not image classification, but image generation. None of the faces you see on this slide are of a real person. And for the earlier faces, you can maybe see that more clearly, but the later faces are quite convincing. These pictures have been generated by a computer to create a convincing face. And I think the result speaks for itself, and the most recent in this is 2018, and in the last 5 years, the field has only advanced further. This extends not only to images, but also to videos. This is not Tom Cruise. This is instead another person. No professional animator was used to create this video, but instead a deep fake neural network was used to take a video of another person and make a convincing video as if it were Tom Cruise. Deep learning also has been able to play various games at a very high level. This includes video games, board games, card games like poker, and so on and so forth. One notable example is the game of Go. Chess, for quite some time, computers have been able to defeat humans using older artificial intelligence algorithms. Garry Kasparov was defeated by Deep Blue in the 1990s. But Go, an Asian game, actually took much longer for computers to defeat humans. Not until 2018 did AlphaGo, which was a computer based using deep learning, defeat the world's best Go players in a head-to-head match. It's also superior at games like chess. Of course, the old computers are better at chess than we are also, but the new computers are better than the old computers. Language translation is another thing that deep learning can do reasonably well. I don't know Polish, I know English, but for all of you who know both English and Polish, you can look at this translation, and I've been told that it's a reasonably good translation. I think sometimes it won't be as good as, it will be it's a good starting point. I think Google Translate uses deep learning, and it's often a good starting point, at least, for a translation. And finally, we have large language models, which I think has been creating a lot of excitement recently. ChatGPT is a large language model that can seemingly have a very convincing conversation with a user who will type questions in, ChatGPT will answer, and you can even have a back and forth. And this is very impressive. Here I give as an example of a prompt, briefly explain ChatGPT, so it's asked to explain itself using a metaphor that would resonate with an audience of stock market investors and avoiding artificial intelligence jargon. And so ChatGPT, I think, does a good job of this complex task that involves understanding metaphorical language, what words are included in jargon, and its target audience. So how does deep learning do all of these fascinating things? Well, we'll start with the simpler examples, and then we'll work our way towards some of the more difficult tasks. For image classification, deep learning takes a neural network, an artificial neural network, and it takes an image as input, and as output, it has output neurons. So some of the neurons in this artificial neural network are assigned to different types of objects, like an egg, a dog, an apple, a bear. All the different objects have their own output neuron. Each of those output neurons will output a number between 0 and 1, representing the probability of that object being in the image. That value will be compared with the true value, which a human will have labeled the image. A human will have looked at the picture first and have said whether it has a cat, a dog in it, etc. And the neural network will be rewarded or punished according to how it did. And in particular, neurons and their connections that are responsible for the correct output will be rewarded. And if it's an incorrect output, the neurons, the connections between neurons that are responsible for that incorrect output will be penalized and will be changed accordingly. So those same principles for image classification of neurons changing according to credit and blame are going to extend to the other applications, but the other applications are going to be a little bit more complex. We talked about image generation, that example of creating fake faces. You're actually going to train 2 neural networks to perform this task well. You could think of this as a game between an art forger, who's trying to create a fake Leonardo da Vinci or a fake face, and an art expert who's trying to catch the art forger and identify, this is not a real Da Vinci. The art expert, or the discriminator, will be given a real face and a fake face, a generated face, and it will have to identify which face is real and which is fake. The art forger creates the fake face for the discriminator. If the discriminator gets the answer correct, the discriminator is rewarded, and the art forger, the generator, did not do a convincing enough job, and so the generator is penalized. If the discriminator gets the answer incorrect, then the discriminator is punished, penalized, and the art forger, or the generative network, is rewarded. In this way, both networks improve with each other, and over time can create very convincing images. And perhaps the most not perhaps, but the most complex of these models are the language models. So how are these language models trained? Well, these language models are trained in phases. The first phase, which is called pre-training for the large language models, it basically is going to read the internet. It's going to read all sorts of different texts, all sorts of different books, in all sorts of different languages. And words will be blanked out. And the neural network will have to predict what word fills in the blank. The cat sat on the mat, chair, rock. All of these could fit inside that blank, and all of them are acceptable words. And so the neural network will learn to predict this, and in order to do so, must understand what words are nouns, verbs, and so on and so forth. But it doesn't just have to have a grasp of grammar to perform this task well. It also must have some idea of, or some capture the relations between words, right? The blank empire was ruled by Julius Caesar. In order to fill in this blank with the Roman Empire, one must understand, or one must know that there is a relationship between Julius Caesar and the Roman Empire. So that's the first step, or the pre-training in a large language model. And that process is very expensive, costs millions of dollars in power costs alone. You think about a computer is plugged into a wall, it's going to add a little bit to your power bill, but not a ton. But they plug these servers into the wall and they have to train for weeks. It costs millions of dollars just to do that pre-training step for a large language model like ChatGPT. After the pre-training, then the neural network is divided into 2 neural networks. Sort of like you had the 2 neural networks, the art forger and the art expert. One neural network will be called the reward network, and the other will be ChatGPT itself. The reward network will learn to imitate human preferences in conversational tasks. And it will learn to do this because humans will be given questions and different answers to those questions, and will rank those answers. And then the reward network will try to predict the human ranking. So it will try to imitate the human preference. ChatGPT will then be trained using the reward network. ChatGPT will be given questions. ChatGPT will create multiple answers, and the reward network will tell ChatGPT how it did. So there are two neural networks. I think it's important to note here that whoever's labeling the data, whoever's ranking the answers, has a large impact on ChatGPT or whatever large language model is being trained. This could include biases according to political persuasion or other various biases as well. So that's something important to think about and maybe even control for in the future. So why is deep learning different? Many of the things I've talked about are actually similarities, things that we can do, we've been able to do for a long time, but computers have only been able to do recently. What are the differences between computer thinking and human thinking? Well, there's some small differences and some big differences. First of all, computers have some advantages over us as humans. Computers are tireless. You plug a computer into the wall and it keeps on running. Probably all of us have had the experience of studying for an exam or working on a project, and we get tired and we have to sleep. We can't keep on studying, at least not effectively. Computers are not only tireless, but they are more flexible in their inputs and outputs. We interface with the world around us, we interact with the world around us, we experience the world around us using our five senses. That includes our sight, our hearing, our taste, our smell, and our touch. And we have two eyes, and we experience a three-dimensional world. If you're trying to train a self-driving car, you don't have to give the self-driving car 2 eyes, you can give the self-driving car 10 eyes. Cameras all over the car, and have the self-driving car learn how to use all of those eyes together, something we could not do. But it's good that computers are tireless because they require a great deal more data than we as humans do. I mentioned for image classification, 1.4 million images were used. That's a lot of images, and if you had to study that many images to identify different objects, you would probably still be studying that, and you wouldn't be here today. To give you an idea, I didn't know what a gibbon was until recently, so I gave this as an example. Maybe some of you know what a gibbon is, but here's a gibbon. Here's one picture of a gibbon. From this one picture, you can imagine a gibbon in different postures, and you can imagine a lot of different gibbons, and you have some idea of what a gibbon is, just from one picture. Humans learn much more efficiently. They require less data. We're not tireless, but we don't need 1.4 million images to learn what a gibbon is. Computers, on the other hand, needs lots of images. And as someone who has worked in the field, engineering these neural networks, one of the first things you think about when you're presented with a new task for a deep neural network to perform is how to make your data set bigger. And this includes simple data augmentation techniques. Here we have a picture of a duck. And then we have the mirror image of the duck. So one picture has been turned into two pictures. And then we have the duck tilted. And then we have cropped, zoomed in on the duck. You can zoom in many different ways. Different color schemes, blurs, adding random noise. All of these are ways you can make one image of a duck into many images of a duck. Now, this is very useful for computers. If you're trying to train a deep neural network to learn how to identify ducks, this process is very important. But if you think about it, if you're trying to teach a child what a duck is, would showing the child the same duck, just with these slight changes, be helpful? No, it wouldn't. So there's clearly something different, right? Once you've shown the one image of the duck, if you show the flipped image of the duck, that's not particularly helpful to the child learning what a duck is. And I'll suggest that A fundamental difference is in thinking outside of the box, in creativity. Computers can think inside of the box, I will claim, but not outside of the box like we can. I'll give you an example. Here I have 4 gray parallelograms on this slide. And then I have a green parallelogram and a red parallelogram. Suppose you train a computer using the 4 gray parallelograms. Well, intuitively, we can look at the green parallelogram and we can see that it is in between sort of the gray parallelograms. It is not the same as any of the gray parallelograms. It is a new parallelogram, but it is similar. The computer is much more likely to correctly identify the green parallelogram than the red parallelogram. The red parallelogram is not like anything in the gray parallelograms inside the data set. It's not inside the box. And so if you're training a neural network to identify parallelograms, you need to expand the box. You need to give it more parallelograms to perform well. Another difference is computers can be tricked. We can be tricked as well, but how computers are tricked and how we are tricked, it's very different. Here are 2 images of a panda. To our eye, they are identical. It turns out that the one image of the panda, the image on the right, is strategically modified to trick a particular neural network. We can't even tell the difference between these 2 images of a panda. But the image on the right, the neural network predicts, is a gibbon, which I showed you before, not a panda. And it predicts so with 99% confidence, whereas it was only 57% confident that the image on the left was a panda. Just a reminder of what a gibbon looks like. Here's another example, or what's called an adversarial example, designed to trick a neural network with stop signs. And this example could be concerning if you're thinking about buying a self-driving car, for example, right? Both of these are stop signs, but at least one neural network has incorrectly identified one of the stop signs as a sports ball. But what about state-of-the-art large language models like ChatGPT? They seem to be doing something much more similar to what we are doing. So we'll talk about that a little bit more. First of all, I want to say that these state-of-the-art large language models like ChatGPT, they also think inside the box. And I'll give you examples to prove this in a short little bit. But also, they only have access to symbols, to the words. Greek philosopher Aristotle says that spoken words are symbols of mental experience, and written words are symbols of spoken words. Just as all men have not the same writing, so all men have not the same speech sounds. We have English, Polish, different languages. But the mental experiences, the ideas, which these directly symbolize, are the same for all, as also are the things of which our experiences are the images. From this quote of Aristotle, we get 3 things: word, idea, and thing in reality. We use words to refer to our ideas, and those ideas correspond to things in reality. The computers only have access to the words, and I will show you some examples to illustrate this as well. They only have access to the symbols. They can manipulate the symbols impressively and well, but they don't have the underlying meaning. Computers have been good at manipulating symbols for a long time, but only until recently have they been good at manipulating human language, fuzzy symbols, if you will. Computers previously have only been able to manipulate precise symbols. You think about math, 2 + 3 = 5. Those are symbols, and the computers have been able to manipulate those symbols very well since computers were first designed. Search and replace in your computer. Computers have been able to do that for a very long time. All computer code, if you know how to code in any different programming languages like Python, Java, these are precise languages. They're called languages for a reason. They have similarities to human languages, but they also have differences. They're what you call context-free grammars. They don't require any context. They're perfectly precise. These are all precise symbolic manipulations. But human language is fuzzy. He looked at the dog with one eye. This sentence has multiple different interpretations, multiple different meanings. It could mean he looked at the dog using only one eye, or it could mean he looked at the dog who has only one eye. This is an example of the ambiguity in human language. And until very recently, computers have struggled with this significantly. But ChatGPT has, I think it is fair to say, made a significant stride in overcoming the fuzziness of human language. However, two issues still remaining. ChatGPT thinks inside the box, and it still, even though it can deal with fuzzy symbols, can only work with symbols. So I'm going to give you some examples to illustrate this. Just a quick disclaimer, ChatGPT is updated, so all of the examples, or most of the examples I'm about to show you are actually from this month, so they're very recent. But ChatGPT, they've been making the box bigger. It's been getting better. And so just because I give you an example of how to trick ChatGPT today that worked earlier in this month doesn't mean it will work 3 months from now, for example. However, I hope to show you how to trick ChatGPT yourself. I hope, if you enjoy doing that sort of thing, I hope to show you, that sort of technique to trick large language models like ChatGPT. Okay, so here's my first example of tricking ChatGPT that shows us a couple different things. If 5 ampersand, that's the ampersand symbol, if 5 ampersand 5 is 10 and 7 ampersand 9 is 16, what is your best guess for 3 ampersand 8? I asked ChatGPT this question. Of course, I intended the answer to be 11. ChatGPT predicts the result as 0. I intended the answer to be 11 because the idea I had not just the symbol, but the idea was that the ampersand would be addition. And when you saw this puzzle, you, because you have an idea of addition and not just a symbol of addition, were able to quickly remap a new symbol and use it for an idea you already had. ChatGPT is working just with the symbols. And the ampersand symbol is used in computer science as what is called the bitwise AND operator. And so it's not able to quickly remap it like we are. And so it predicts that AND should be bitwise and gets the incorrect result of 0. Here's another example. Progo is a nickname I personally use for a famous historical figure who ruled Rome before he was assassinated by his friend. If you absolutely had to guess, who would be your first guess for who Progo might be? I tried to ask it this question several times and tried to force it to answer. It likes to dodge questions sometimes. I couldn't get it to answer. Progo is a made-up word, but I intended Progo to be referring to Julius Caesar. And I think I gave it enough hints that it should have been able to guess that, given that it has, read all of Julius Caesar and all the history and all that sort of stuff. But instead, ChatGPT dodges the question. And again, there's that idea of an underlying symbol or an underlying idea to a symbol. Julius Caesar normally refers to the idea of Julius Caesar, the words. Progo, this new word, does not normally refer to the idea of Julius Caesar. But because we have the idea, we are able to adapt quickly and remap to this new word to correspond to Julius Caesar. Here's another example. If you subtract 7 from another multiple of 7 more than 3 times the size, will the result be a multiple of 7? Will it be prime? This is sort of a reasoning task I gave it. It gives a rather long answer, which it sometimes does if it's trying to hide it, if it's a little bit insecure maybe. Well, when you add 2 multiples of 7 or subtract, you will get a multiple of 7. It's a long answer. I want you to focus on the last part of the answer. It says you get 28, which is a multiple of 7 and a prime number. Well, that's incorrect. 28 is a multiple of 7, but it is not a prime number. It has prime factors 2, 2, and 7. But because I'm familiar with ChatGPT, I know that if you give it a question that's inside the box, it's going to get that right. If you phrase it in a familiar fashion, it's going to correctly answer. And so I ask it, is 28 a prime number? A very simple question inside the box. And ChatGPT correctly says, no, 28 is not a prime number. And so ChatGPT isn't always consistent, depending on how you phrase things and this sort of thing, because it doesn't have the underlying ideas, and it's only able to think inside of the box. Francois Chalette is an artificial intelligence researcher from France. He's significant in the field. He's responsible, a major contributor to the Keras and PyTorch deep learning libraries. And these libraries are used by researchers all over the world. They're very impactful. He says, the gap between generating words and generating meaning will prove hard to close, meaning being the ideas, words being the symbols. Generating meaning requires a model of the things being talked about, language as communication, while generating words only requires a model of the structure of text, language as statistics. Francois Chalette also has spent some time fooling ChatGPT. Here he gives a simple riddle, or gives some simple examples to which ChatGPT is supposed to find a pattern and correctly apply that pattern to a new case. The pattern here is you should capitalize the first and last character in the string. Well, ChatGPT fails to perform this pattern, to identify the pattern, and instead alternates. This is another example. Because of time, I will skip this, of Francois Chalette tricking ChatGPT. So Francois Chalette says of the tasks he just gave it, this is all very low complexity, but that's irrelevant to a large language model's ability to handle the tasks. Only familiarity matters, thinking inside of the box. As long as you're dealing with a variation on something the model has seen, you're good. But whenever some novelty arises, something outside of the box, the model can't reason on its own. So large language models, like the other deep neural networks, think inside the box, not outside of the box. In conclusion, deep learning can imitate many human behaviors very impressively using interpolation, or thinking inside of the box, filling in between the gaps, but cannot extrapolate or reason originally for something new. To make deep learning better, you have to make the box bigger. But deep learning on its own cannot make the box bigger, where we can. ChatGPT can masterfully sequence symbols, all without understanding the ideas those symbols correspond to. And so I hope this has helped you understand artificial intelligence and ChatGPT, and the differences and the similarities between how computers think and humans think. Thank you, everyone, for listening, and have a good day.